This is Chapter 7, Section 2. We're going to talk about reaction rates today. This podcast has a chance to be a little more lengthy than some of the other ones we've done. I will show every part of every slide. I won't repeat what's on every slide, but just make sure you get all the information down in your notes. So first off, reaction rates. It is the change in concentration of reactants per unit time. And again, the area of chemistry, we'll be talking about reaction mechanisms and what we're doing today. And it'll look at chemical kinetics. And again, kinetics, that's talking about motion. Some factors that will influence rate. We are looking at the collision frequency of your reactants and the collision efficiency. We'll also look at the nature of the reactants, the surface area, the temperature, concentration, and is there a catalyst present? And we will talk about what a catalyst will do to your reactions. So starting off with surface area, in a heterogeneous reaction, and we will look at the difference between homogeneous and heterogeneous reactions. A heterogeneous reaction, the rate will depend on the area of contact between your substances, and for a heterogeneous reaction, there are two different phases. So your reactants will be in two different phases. That's why we're using the prefix hetero. And an increase in surface area does increase the rate of your reaction. So an increase in surface area increases the rate. Temperature, how will it affect? If you increase the temperature, then the speed of your particles obviously will speed up and you'll have more effective collisions. So the number of your effective collisions will increase the rate. The higher the temperature, the more particles that you have that possess even more energy to form an activated complex, and we will look at the definition for an activated complex here before it's over with. And at higher temperatures, you have enough energy, again, for the activated complex, and a rise in temperature increases the collision energy, therefore your collision frequency. So the higher the temperature, the more energy, the more speed that you have in your molecules, the more collisions you will have. Concentration, again, if you have a heterogeneous reaction system, doesn't just depend on the surface area, but also the concentration that you have. And the example they're given says a substance oxidizes in air, oxidizes more vigorously in pure oxygen. So if you just had air, which again, if you think of air, it's really 70% nitrogen, the more oxygen you can get to it, then the higher the concentration you have of your oxygen, the more oxidation can take place. If you have a homogeneous reaction system, the reaction rates depend on the concentration of your reactants. Again, homogeneous reactant systems will be similar than your heterogeneous. In this example here, it's talking about different collisions, so concentration versus collisions. You're going to want to make sure you understand these. In the first one, it gives one possible collision can occur between reactants A and B. There you have it in the top left. Right next to it, 4 possible collisions. And then the bottom left, 6 possible collisions. And then you have 16 possible collisions in that system. So again, the higher the concentration, the more possible collisions you will have. So again, this is just summarizing that again. So the higher the concentration that you have, then your reaction rate will be effective and it'll have to be determined experimentally. So sometimes our reactions can be increased dramatically. The rate can increase dramatically by the presence of a catalyst. And we will look at catalysts now and in the next few slides we've got going on. A catalyst can change the rate of a reaction without itself being permanently consumed. So it's going to be hanging around. It can affect the friends around it, but it will not be affected itself. So the action of using a catalyst is called catalysis. A catalyst does provide an alternative energy pathway or reaction mechanism between your reactants and products. It can be effective in forming an alternative activated complex that will require a lower activation energy, so less energy needed if your catalyst is present, and it will not appear in your final products but it will speed up the reaction rate of your reactants. So our homogeneous catalyst, it is in the same phase as all of your reactants and products in the reaction system. So if you have a homogeneous catalyst, it is in the same phase as what you're starting with. A heterogeneous catalyst will be in a different phase from your reactants. And metals are often used as a heterogeneous catalyst. Right here, make sure you get this in your notes. It is looking at the comparison of different pathways for the decomposition of H2O2. That's hydrogen peroxide by various catalysts. So if we concentrate on what we're seeing here, I'm just getting my different colors going on. Here at the top, we have an uncatalyzed reaction. So you are breaking down hydrogen peroxide. You see you have a much larger energy curve going on there. The one right below it is chemically catalyzed. So we've got the iodine ion going on in here. So this is going to be a homogeneous process. So if they decide to use the iodine ion, we are lowering that activation energy to 58 kilojoules per mole to make it happen quicker and with less energy. And then if you use an enzyme catalyst to go through here, you can see that activation energy is lowered even further. And then there at the bottom, we have a heterogeneous process. So H2O2 is going to be more than likely in the liquid phase, and those middle two curves are going to be in the liquid phase too for your homogeneous process. At the bottom, they're using manganese, looks like manganese 4 oxide to do a heterogeneous process, and you can see we have a couple different activated complexes going on, and the curve, it is going to happen with less energy, much quicker going on with it. So we are going to look at a series of experiments that will tell us the how our reactant affects the reaction rate, their concentration. So the equation that relates reaction rate and concentration of reactants is called the rate law. It is called the rate law, and this will be given at specific temperatures. In this example right here, we have hydrogen and nitrogen monoxide that are reacting to give nitrogen gas and water or steam. It's in the gas phase, and the initial reaction rate is found to vary directly with the hydrogen concentration, because you can see based on our coefficients that we've got going on right here, the rate doubles when hydrogen is doubled, but it triples whenever hydrogen is tripled. And we are looking at your coefficients out front for that. So the rate is proportional to your hydrogen concentration. The initial reaction rate is going to be found to increase 4-fold when nitrogen monoxide is doubled and 9-fold when it is tripled. So the rate is going to be proportional to the nitrogen monoxide concentration doubled. Just a refresher on some of this right here. Whenever you see your element in the brackets like this, that is referring to concentration. Now, the information that they're giving right here, they're saying if you could go in and physically see the experimental data, the results from this reaction taking place, and look at its data, that's where they are getting the when does it double, when does it triple, what's going on. And before this lesson is over, we will look at data so that you can figure this out yourself. So again, on this, some of the information they're given, it is based on rate data, which you are not looking at. So for now, we're just going to look at the information they have so that we can get to what our rate equation would look like for this particular example. So because R is proportional to the hydrogen concentration and nitrogen monoxide concentration squared, it is proportional to their products. So now we're getting to how you would set up this equation if you actually wanted to calculate the rate for the equation. And here we introduce a constant K, and you would have a constant that would go in here so that rate would equal the constant times these concentrations, how they are set up. So the value of K usually increases as the temperature increases, but the relationship between reaction rate and concentration almost always remain unchanged. So the general form for the rate law, you've got R equals a K, which is going to be some constant for that particular reaction, reactant A to some exponent n, reactant B to some exponent m, and again, this is going to be generic for what we have, and it does depend on how many reactants you have and how each reactant alone will affect the rate. So the power of which a reactant concentration is raised is called the order in that reactant. So in this case, the value of N is said to be the order of the reaction with respect to A. So the reaction is in the nth order in A. Nth order in A, and you will see some examples so that we can apply, well, what order is this reactant in? An order of 1 means the reaction is directly proportional to the concentration of that reactant. An order 2 means it's directly proportional to the square of the reactant. If you have an order of 0, that means the rate does not depend on the concentration of the reactant as long as some of the reactant is present. So definitely order of 1, order of 2, and then make sure you understand the order of 0, and we will apply it in an example. The sum of all the reactant orders is the order of the reaction or the overall order. In this example, nitrogen dioxide and carbon monoxide will react to give you nitrogen monoxide and carbon dioxide. They are telling you that the rate of this reaction is going to be dependent upon the nitrogen dioxide that's reacting to the second order. So it is second order in NO2. It will be 0 order in carbon monoxide because, again, you haven't seen the rate data, you don't know what it is. We're just getting you set up so that you can set up your own rate equations here pretty soon. So 0 order in carbon monoxide. Notice carbon monoxide was not included in this rate equation based off of whatever data they had gathered. And overall, it is second order because the only reactant we have to look at is the NO2. The orders in the rate law may or may not match the coefficients in the balanced equation. So in this case, it matches the total coefficients of 1 and 1, but notice the second order does not match the coefficient for the NO2 itself. So again, it is based on rate data that would be looked at. So now we're looking at the specific rate constant. That is the K that we introduced. It is proportionally constant to relating the rate of the reaction to the concentration of the reactants. So once your reaction orders are known, the value of K must be determined from experimental data. And this value is for a specific reaction, and it can change for different reactions even under the same conditions. The unit of K will depend on the overall order of your reaction, and it does not change for different concentrations of reactants or products for a specific reaction. So the value of K for a reaction will remain the same throughout the reaction and does not change with time. Again, it is for a reaction at a specific temperature. If we increase the temperature, the value of K also increases. And K changes if a catalyst is present. So your reaction rate, you would expect it to happen faster in the presence of a catalyst because most catalysts speed up a reaction. You actually have a few that would slow it down, but most of them will speed up the reaction, which means K would change. Let's look at an example problem. So now we're going to get into actually showing you some real data. So we've got hydroiodic acid that is being broken down into hydrogen and iodine gas. This is already a balanced equation. And if an experiment were run, and you're going to want to write all of this in your notes so that you can go back and analyze data as you're working through examples later, we have the concentration of the reactant, hydroiodic acid. Notice, again, concentration, we use the brackets, and concentration, that is molarity. Molarity is moles per liter if you're talking about your solutions. So, in the 3 different experiments, they changed the reactant concentration from 0.015, they double it, and then add another 0.015 to it in the 3rd experiment. And we are watching, how does the rate change? Notice this is molarity per second. How does the rate change as our different, in this particular case, how the reactant concentration is changed? So we're going to write the rate law for this reaction. So you're going to have to determine some of this stuff yourself. Find the value in units of the specific rate constant. So let's get busy with that. Make sure you have all this data written down so that we can move into you setting up your rate reaction. Your reaction rate equation. So for this one, since there is only one reactant, our general form will be the rate is equal to a constant times hydroiodic acid, its concentration to some power n. We have to figure out what that power of n actually is going to be. So if we look at a concentration ratio, they have decided to take experiment 1 and 2 and compare their data. We have thrown in the concentration for experiment 1 versus experiment 2. And again, this one, the concentration was doubled. That's why you see the concentration ratio is 2. If I look at the rate ratio, so now they're taking the rate data. Again, we are comparing apples to apples here. I took experiment 1 and 2 here. I'm also taking the rate for experiments 1 and 2 here. And when I look at the rate data, notice that the rate ratio, even though the concentration was doubled here, the rate increased by 4-fold. So if I take that and now I divide this out, 4 divided by 2 equals 2, because we do have to account for we increase the concentration by 2. The overall rate actually doubled with the concentration of HI. So our rate law would be R equals a constant HI squared. So again, we did take information from both of these. The rate technically doubles whenever the concentration doubles. So we do have to account for some of those. You might see some experiments later on, or you will see some experiments later on where these numbers will change around some, and you'll have to do this initial math first to get your rate. Now, if we want to find the concentration of K, we're going to pick just one of these experiments. At this point, now that you have your setup and you know what your exponent is here for the reactant, which is squared, you can take any of the 3 experiments and use the concentration and rate out of those experiments. On the next slide, it looks like we're going to use the first experiment. So we're going to use the concentration of HI as 0.015 and the rate out of that first experiment. We're going to plug all of this into here. We're going to rearrange it and find out what the value of K is. So we have rearranged the equation to get K by itself. We plugged in the rate and the concentration of HI for the first experiment, and we see that our final answer for the value of K is 4.9, and it would look like M times S. So that is 4.9 per molarity second, the way this would be written. Again, units are going to be important. Please pay attention to how units fall out, because your units will change for your constant based on whatever the setup is for your rate equation. So please understand how these units will come to be. So if we have M over S for our first one divided by once you double your concentration, that would be m squared. One of these does cancel out with this one on top, so it is m times s when you get there in your answer. Okay, now we're dealing with two reactants. We're just keeping it simple here, saying A plus B yields C. And in these three experiments, they're going to give you how the concentration of A either stays or changes, concentration of B also, and then your rate. And we have to find the rate law for the reaction. As I look at these right here, we are going to have to compare when we're finding our information for A and our information for B. Notice in the first two experiments, A, the concentration doesn't change. So that would be really good to use experiment 1 and 2 for B's purpose. And then for A itself, I notice B stays the same for experiment 1 and 3. So that would be good to use that information for reactant A to figure out what's going on with rate and to find our exponent there for A. So again, we are going to have to be a little more picky here with which experiments we're using to find our information, because we don't want, when we set this up, for A and B to be changing at the same time, because you're not sure which one has more effect on rate. So when we're finding the effect for B, we will have to use experiments 1 and 2 because A stays constant. When we're finding the effects for A, we will have to use experiments 1 and 3 because B's concentration stays constant. So here's our general rate law. Again, we have two reactants. So we're going to see what order A and B are going to affect our rate. To find M, again, we're going, and this is for reactant B. We're comparing experiments 1 and 2 because A stays the same. So experiments 1 and 2. Notice if we put the higher number on top for this right here, but you see B doubles between here. That's the concentration ratio. Now we're going to look at the rate ratio, and you can see that I just want to point out one thing here. Again, it's 1 over 2, and you have to keep it as 1 over 2 for the rates. You can see that both of these, it looks like, is an order of 2. Well, 2 divided by 2 is 1. 2 divided by 2 is 1. So M is first order, and the reaction is first order in B. So that'll be B raised to the first power, but you don't actually write a 1. But you have to leave the B in there since it is first order. To find N, we'll look at experiments 1 and 3 because B's concentration stays the same. So again, A3 over A1, our concentration ratio is 3. The rate ratio, again, we're doing reaction 3 over 1 or experiment 3 over 1. And you can see that that rate jumps by 9. So 9 divided by 3, or it's not 9 divided by 3, it's going to be 3 squared is equal to 9. So we are raising it to the power, so N equals 2. The reaction is second order in A. So I know I've explained the previous one wrong at this point. Again, I just want to clarify that for the previous one that we were looking at. Because I said 4 divided by 2 or 2 divided by 2. It even in a previous one, again, sorry. But 2 to the first power is 2. 2 to the second power is 4. And I was saying 2 divided by 2 or 4 divided by 2 in a previous one. It is based on the order. So in this one, 3 to the second power is equal to 9. That's why they are saying second order here. So our final rate law for this particular reaction is R is equal to, looks like the equal's missing, a constant, A to the second order times B, and the overall order of this reaction is third order. 2 plus 1 is 3. We rearrange it to find out what our constant is. They are picking, let's see, this would have been experiment number 1. So in experiment 1, the rate is the 8 times 10 to the negative 8th. Concentration of A was 1.2, concentration of B was 2.4, and we're plugging all of that in. Again, you should be able to do the math on this, double check it in your calculator. If I'm looking at units, again, we got M over S times M squared, that's for the A, times M, which is for the B. We see one of these M's canceled, so we are left with 2.3 times 10 to the negative 8th over molarity squared times second. So that's the set of units for this particular rate constant. Getting into reaction mechanisms, the form of our rate law will depend on the reaction mechanism. Is it a single step? Is it multiple steps? And the reaction rate of that step is proportional to the product of the reactant concentrations, each of which is raised to the stoichiometric coefficient. In this example, A plus B yields 2C. The reaction rate in the forward direction is the constant in the forward direction, the concentration of A times B. Again, both of these, the stoichiometric coefficient is 1 and 1. That's why you see 1 and 1 for here. If I were to turn this around, 2C yields A plus B. Well, in the reverse direction, it would be K in your reverse direction times C squared, because that is its stoichiometric coefficient. If a reaction proceeds in a sequence of steps, the rate law is determined from the slowest step because it has the lowest rate. And the slowest step is the rate determining step. You will have to do some of this too within this section, and that is important. So your rate determining step will be your slowest step. So looking at another example, nitrogen dioxide, we've seen this reaction already, but now we're going to break it into the two-step mechanism that it has. Here's its mechanism. The first step is considered the slow step, and then you have your fast step, which is the second step. So step 1 is your rate determining step, and the rate law would be your constant times NO2 squared. And again, it is squared here. They have taken the NO2 and separated it out, but it is NO2 squared. So looking at another sample problem, nitrogen dioxide and fluorine react to give us NO2F. A proposed mechanism. First step again is going to be our slow step, so that's the first step, and then the second step gives us the actual NO2F, which is the fast step. And we want to identify the rate determining step, which will be step 1, and write an acceptable rate law. As I look at this one right here, this is our final reaction there at the bottom between the two steps that we have. We have an intermediate, which is the F, so we will mark out our F, which is an intermediate, and we'll write the rate law from step 1 since it's the slow step, and you get K times the concentration of NO2 and F2. Both of those are to the first power. In another example, between X and Y, here again, it's a fake setup here, and we'll write the rate law for the reaction, and then determine the effect of each of the following on the reaction rate. So what if we doubled the concentration of X, doubled the concentration of Y, or used 1/3 the concentration of Y? So we have several things that we're going to look at here. Make sure you get this written down as we go through the last few slides here to find out what these are going to be. So write the rate law for the reaction is going to be first. As I am looking at this, we have two reactants. We don't have any other information to look at, so it looks like it's first order in X and second order in Y. So it is a single step, so first order in X, second order in Y. And we were told what would happen if we doubled the concentration of X. How would that affect our rate? Well, it would look like this. So notice where the 2 actually goes. So it's not x squared, but it is 2 times x since we're doubling the concentration of x. That's what it would look like. If we were doubling the concentration of rye, it would actually increase the rate 4-fold, because once you put in your 2 here, that also gets squared whenever you follow through with your math. So 2 squared is 4. That's why they're saying 4-fold. And if you use 1/3 the concentration of y, it would look like this. So it would reduce your rate by 1/9, because once you do 1/3 squared, that would give you 1/9. So again, a lot of rate information in this one, looking through the different steps that we do. I hope you got it all down.